Hello. Um, Today we're going to talk about something a little different. Everybody else talks about how to optimize your Rust program to make it faster. Um, we're going to talk about how to make it slower. At the very end, we'll do a little bit of discussing about how to make it run faster again. A little bit about me. I'm an open source maintainer. My most important package is FastLem, which is a genomics package that uses Rust and Python for genome-wide association studies. Previously to that, I was a research programmer for Microsoft Research, but I also sometimes go off on tangents. And in this case, it's a tangent that got me interested in learning about Turing machines and some new results related to Turing machines. Um, we're also going to learn something about large numbers, and at the end, we'll learn how to not just make programs run slow, but some ideas on how to make them run fast. For all of this, the challenge is going to be set up about how to make short Rust programs with very long running times. And in each case, we'll define what we mean by a short program and what we mean by a long running time. And we'll do that via a series of what we'll call rule sets. So let's move on to the very first rule set. In this rule set, anything goes. So if I asked you how to make a Rust program that's short and runs for a long time, what would your idea be? And you might think that what you'd want to do is an infinite loop. And indeed, that's an excellent way to do to meet the criteria. And in Rust, this is what an infinite loop looks like. So that does what I said. It's what I asked for. It's very short. It's nice that it takes negligible memory. But the one problem with it, maybe, is that it doesn't halt. So we might want to change our criteria so that we also require that our programs stop. And let's add that and call that rule set 2. So in rule set 2, our programs have to halt, but we still have this requirement that the amount of memory we use is bounded. And a nice way to approach this is to have is to use nested fixed range loops, and in Rust that looks something like this. We'll have a program here with 4 nested loops with 4 loop variables, and each loop variable will go from 0 to the maximum unsigned 128-bit integer. And just for fun, on the inner loop, every 1 billion values, it'll print so we can see how things are going. So let's analyze this. If we want to know how often we run the inner time there, it's about the maximum of 128-bit integer times that max, times that max, times that max, which is 340 billion billion trillion to the 4th power, which is 10 to the 154 steps. And if we assumed we had a computer that could run as fast as the kind of theoretically fastest computer, one that can take 1 step in each Planck time unit, that computer could run at 10 to the 50th steps per year. If we put that together, then we can run 10 to the 104, then this program would take 10 to the 104 years to finish running. So scientists think that our universe will be around for about another 10 to the 100 years. We put those two together and we see that we've got a program that will run 10,000 times longer than the length of the universe. And another consideration is these nested loops only use 64 bytes of memory for the 4 variables, but this computer has 64 gigabytes, and if we were to use all that memory for variables, then we could write a program in this style that would run for 10 to the 165 billion years of computation. So looking at our criteria, this program halts, it's short, and it uses bounded memory. And the reason I put a question mark on bounded memory is because maybe it would be interesting to relax that constraint and see what we can do if we allow unbounded memory. So let's do that, and we'll call that rule set 3. So in rule set 3, our program must halt as before, and we've got this new thing, unbounded memory, and we'll require it to be initialized all with 0, so we can't encode anything in there. And the way we'll look at this, at least at first, is we'll look at it not with a regular computer, but with an abstract computer called a Turing machine. And a Turing machine is this mathematical construction, and one of its parts is that it has an unbounded tape. So consider that a tape running in both directions for as long as we need, starting all with zeros, and each cell on the tape can only hold a 0 or a 1. If you look at the little triangle on the picture, that's the read-write head. So it can read a 0 or a 1. It can then write into that same cell a 0 or a 1, and then the head can move one position either to the left or to the right. We also allow our this abstract computer to have an internal state. And this first one, we're going to require it to have just 5 possible values. So that's like a Rust enum with values A, B, C, D, and E. We're also going to have an additional state called H that stands for halt. And we don't count that when we're counting how many states we have. So this still only counts as 5 state. Putting that together, a program is just a table that goes from the 2 possible input symbols, 0 or 1, and the 5 possible states, A, B, C, D, and E, and gives a triple. And the triple is what value to write, whether to move left or right, and what state to move into. And if you look at this sample program, you can see that if we read a 0 and we're in state E, then we'll move into the halt state. So that just shows how we make our programs terminate. Let's see a Turing machine run a little bit. We always start in state A. We have a program. The head is reading a value. It reads a 0, so we look in the table, and if we have 0 in state A, then we do 1 RB. We write a 1, we move to the right, and we move to state B. And indeed, that's what we do. And now we're in state B, and we read a 0, so 0, state B, we should write a 1, move to the right, and move to state C, and so on. I won't keep writing the program, but let's think about how we can look at the results of the program. At each step, we have a generation of our tape. We can think about the previous generations and keep running and see what the generations to come are. This isn't something that we necessarily can store in memory, but at least abstractly, we can think about each generation, each step of the tape. And if we want that picture to be a little prettier, we can turn all the 1s into some color, here orange, and we can turn the 0s into some background color, and that gives us a nice visualization of what the Turing machine is doing step by step by step by step by step. Let's run it a few more steps. And the very bottom row you see there means there's a bunch of 0s, and then a block of 1s, and then a bunch more 0s. We can widen it. This isn't anything to do with the Turing machine itself. This is just me stretching out the previous diagram so it fits the screen better. And we can run more steps. So here we're at 100. There's 100 steps, 500, 1,000, 5,000, 10,000, 100,000, a million, I'm accelerating it, 47 million, and then some, and then it stopped. So what we saw, kind of surprising, was that this little program that we see right in the corner runs for exactly 47,176,870 steps, and then it just stops, which I find remarkable. Even more remarkable is the fact that there is no halting 5-state Turing machine that runs any longer. That amazing fact was proven by a group of amateur researchers organized at the site Busy Beaver Challenge, bbchallenge.org, just a couple years ago. And a preprint of the research paper showing their results came out just 2 days ago. It's easy to see that the program runs for 47 million steps. What's very hard to see is that there's no other comparable program with just 5 states that doesn't run longer. And that was the key to their mathematical proof. They were able to mathematically prove it, and that proof was computer verified, so we can have confidence that it's true. So I said we were going to write Rust programs that run longer and longer, and now I've been only showing you a Turing machine. But in fact, it's very easy to turn a Turing machine into a Rust program because it's very easy to write a Rust interpreter for a Turing machine. Super straightforward. It's fast, it's simple, it uses a fixed amount of memory, except that somehow we have to model this infinite tape, and the way I chose to do it was to have two U8 vectors, one going in the non-negative direction and one for the negative direction. And that worked great, and that gave me a program that halts, which was one of our requirements. The program is very short. We can just look at the Turing machine table there. That's the whole program. It uses this new Luther constraint that we have unbound memory, but notice the amount of memory actually used, if it halts, will still always be finite. But kind of disappointingly, it only ran for 47 million steps, which wasn't even nearly as far as we got with rule set 2 with our loops. So the next question is, can we change something about what we did to let us create a Turing machine that runs even longer? And remarkably, all we need to do is add one more state. Before we had state A, B, C, D, and E, and now we have state A, B, C, D, E, and F, and a new program. And if we run this program for 284 steps, this is what the Turing machine tapes will look like. Let's run it a bit longer. So 100,000 steps, 1 million steps, 10 million, 100 million, 1 billion, 100 billion, 1 trillion, 10 trillion steps. And then the video stops. So did this program really run for exactly this round number of 10 trillion and then halt? The answer is no. The abstract program would still keep running. I just got tired of doing the visualizations and told it to stop at 10 trillion. So how far would this run, and would it halt? Yes, this simple program halts at 10 to the up arrow 15 steps. That's notation that means 10 raised to the 10 raised to the 10 raised to the 10 stacked 15 times. That's an operation called titration. So let's review a little bit exponential notation. 10 to the first power is 10. 10 to the 100th power is 10 billion. 10 to the 10 to the 10 is 10 raised to the 10 billion, so that's really, really big. 10 to the up arrow 4 is 10 to the 10 to the 10 to the 10. That's more than the number of atoms in the observable universe. And we can say 10 to the up arrow 15 is a number so big that it's annoying to represent an exponential notation. So that's pretty big. 3 years ago, one of the researchers involved in the Busy Beaver proved that this Turing machine halts after running 10 to the up arrow 15 steps. And that was a remarkable thing because it couldn't obviously just run it. What hasn't been proven, and may never be proven, is that it's possible that there's some other 6-state Turing machine that halts and runs even farther. We just don't know. But in any case, this Turing machine is easily interpreted in Rust. And we can just run it. And if we do that, then we get a Rust program that halts, that is short, that uses unbounded memory, that runs for 10 to the up arrow 15 steps, which is way more than we got with the nested loops we saw before. But the only thing, and I'd say the only downside to this, as far as our what we might want, is it's very hard to see that it runs that far. The effort involved in proving it was quite extensive, so it's not understandable. So that brings us to our next rule set. Let's see if we can create a plain Rust program that halts, that has this unbounded zero initialized memory, but that we can also understand. And specifically what we're going to do is we're going to try to compute 10 to the up arrow 15 without using a Turing machine, just using plain Rust, in a way that it's obvious that it's doing the right thing and taking at least that many steps. Our strategy will be based on something that you may have seen before, and that's the way that it's possible to define addition in terms of the increment operation, and then define multiplication in terms of the addition operation, and then define exponentiation in terms of repeated multiplication, and finally this titration we can define in terms of repeated exponentiation. And we'll look at the first step in that stack. First is increment, and the thing we'll need for this to work is something to represent our unbounded memory, and for that we'll use an infinite precision integer package called num bigint, and we'll define an increment function, and it'll have a mutable reference. That's an input-output variable in Rust called increment accumulator. We'll send a big int in as increment accumulator. We'll just add 1 to it, and then it'll be available after the program finishes with 1 greater value, and we can see that run. We can just set a big int to 4, increment it, and then print the result. And if we do that, we'll see that the increment of 4 is indeed 5. So increment is pretty straightforward. The important thing here is that we're using these unbounded integers. Within our function, in this case increment, we're going to restrict what operations we can do. So the only things we're going to allow is initialization to 0, to do an in-place increment or decrement, and to do a comparison, but only comparisons with 0. Specifically, we're going to prohibit any copying or cloning. We're not going to allow arbitrary arithmetic because, among other things, that often creates temp values, which would require a full copy or clone. So no other arithmetic. Okay, we have increment. Let's see how we can use how addition can be defined as repeated increment. Pretty straightforward. we have some small number a that we want to add to our add accumulator, which is a big int, and all we have to do is do a loop a times, and each time in that loop we'll do our in place increment to add accumulator, and then at the end add accumulator will be a more than it was before. So we'll have added a to add accumulator. Notice I didn't call the increment function that we defined previously. Instead, we just inlined it manually, and that makes it easier to see what we're doing. Okay, this is the most important slide to understand what we're doing here. And that's, we're going to define multiply as repeated addition. So we have a that we want to multiply into our multiply accumulator. And the first thing we're going to do is set our add accumulator to 0, and then we're going to loop multiply accumulator times, and then each time within that loop we're going to add a to the add accumulator. So if we do that, multiply accumulator times, then add accumulator will be the product of a and the original multiply accumulator. Then at our very last step, we'll move add accumulator into multiply accumulator, so we get the return value that we want. And notice that this is a move, not an allocation. We're using Rust's move semantics, so we're not doing a clone or a copy there. I need to explain what that countdown is. It's a trait method that I defined on top of the big integers. It creates an iterator so that on each time it's called, it'll decrement the big integer it has by 1, and if the value is not 0, it'll return some, just the placeholder unit value. So it'll return some all those times every time it increments and it's not 1, and when it finally hits 0, it'll return none, and the iterator will stop. So this is a way for our for loop to count down whatever our multiply accumulator is, that many steps. I'm going to skip exponentiation because it works the way you would think given the multiplication, but let's look at the operation on top of that, the titration. So we have our input A, and we want to up arrow it to the power of up arrow it to ttrate accumulator, and then return the result in the ttrate accumulator variable. It doesn't make sense for A to be 0 here because you can't repeatedly stack a bunch of 0 to the 0 to the 0 to the 0. That's not defined, so we rule that out. Here's what we'd like to do. We'd like to set exponentiate accumulator to 0, and then add 1, because this is going to tell us the power we're going to go to, so we want it to be at least 1. And then we loop tetrate times, and then each time we take a to that power, at first to 1, and then we assign that to exponentiate accumulator. So if a was 2, we raised it to 1, the result would be 2, and that would become our exponent for the next time through the loop, and we'd take 2 raised to the 2, which is 4, and the next time through the loop we would take 2 raised to the 4, which is 16, and the next time through the loop we take 2 to the 16, and I probably should know what that is, but I don't remember. So that all would work great. We'll see a problem. I mean, there is a problem. We'll address it in a second. At the end, exponentiate accumulate will have our answer, and as before, we move it into tetrate accumulate and return. Okay, so the problem is I said we can only do simple arithmetic on these big int types, and here I've got a exponentiated to it, so that breaks our rules. But obviously what we do is we just inline our exponentiate function. that's based like the multiply function, and so on. And that'll give us what we want here. And in fact, this is like real runnable code. You can set A to 2. You can set B to 3, a big int 3, and then we can ttrate A to the 3, and it'll say 2 up arrow 3 equals 16, which is the correct answer. This is straightforward to run. Be very careful if you put in large numbers. If you put in large numbers, things will either run a long time and you won't see a result, or you might run it out of memory because your computer probably doesn't really have unbounded memory. So let's compare this ttrate program to the nested loop program that we had from rule set 2. In both cases, we have four for loops. The difference is back in rule set 2, each of those loops went a static amount of time. Even though it was a very big number, it was always the same big number. And we saw that ended up running the inner loop 10 to the 154 times. Now we still have 4 for loops, but the amount that the loops loop is dynamic and can be one of these unbounded integers. And that's really what allows this thing to keep going and going and going. And you can call it with 10 and 15, and if it didn't run out of memory, and if you had much more time than all the time in the universe, then it would run, it would compute 10 to the up arrow 15 and give the result. Moreover, it would do it by incrementing one at a time, so you can just look at the program and see that this program does at least 10 to the up arrow 15 steps. So where does this get us on our goals? I think it's perfect. It lets us, it's a program that halts. It's still relatively short. It uses this looser constraint of unbounded memory. Now it's running 10 to the up arrow 15 times, which is way more than we got with rule set 2. And compared to the Turing machine program, it's understandable, at least relatively understandable. So I can now give advice for anyone who wants to run their Rust program slowly. If you want your program to run forever, I recommend you use an endless loop. If you want it to only use finite memory and run for an extraordinarily long time, then do a bunch of nested for loops. If you want the very shortest program that you can that runs for even longer than the nested for loops, then emulate a Turing machine. And if you want something that runs the same amount of length, is a little bit longer but is easier to understand, then do this dynamically bounded loops. But maybe you're not really interested in running your Rust programs slower. So let's spend a little bit of time looking at some techniques for running a Rust program faster. And the application I'm going to look at is the visualizer that I used for the examples here. So here's the task that the visualizer has to do. As the Turing machine emulator runs, we can see the values of the tape. Implicitly, there's a history there, but that history might have 10 trillion steps. And on like this Busy Beaver, as the 6-state Turing machine that we looked at, the number of actively used cells would be about 1 million wide. So 10 trillion steps by 1 million wide is too much to hold in conventional memory. Happily, I have a low memory solution to solve this that is only uses memory proportional to the final output image. And our output image is going to be something like 1,000 by 1,000 monochrome pixels, where each value is going to be a value between, each pixel will be just a number between 0 and 255. And each pixel will represent a giant rectangle from the implicit tape history. So that it means that if we had 10 trillion steps, then each pixel represents 10 billion steps. And if it's a million wide, that means that each pixel also represents 1,000 cells. So each pixel represents 10 billion steps by 1,000 cells and is the average of those zeros and ones. So I've got a sensible algorithm that does that. The only problem with it is if I want to run it for 10 trillion steps, it would take 2 years and 3 months to run. So that was too long. So I thought about some optimizations. And I'm going to talk about 3 of the optimizations I did. And the first one is to use SIMD, which is single instruction, multiple data. This is a facility on all modern computer chips, called computer chips for the last 20 years, that lets us do parallel operations. They're mostly simple arithmetic operations, but they only use one processor. So it gives us parallelism on just one processor for as long as we're doing simple arithmetic kind of things. And the first SIMD operation I did is the one that takes this tape that, say, is 1,000 cells, active cells long, and reduces it to 1,000 pixels. So that requires taking a range of the cells and finding their average. And there is a nice SIMD command called reduce sum that can, in one operation, sum 64 of these cells and turn it into one sum, which then we can then do the division to get the average. So reduce sum is a very handy SIMD operation, and I used it. Another thing I need to do from time to time is I generate the picture and I let it get a little bit longer, and then if it gets too long I shrink it back down to 1,000 by 1,000. So that means I have to average rows, 2 pixel rows together, and squish them back into being 1 pixel row. And the main thing I used for that was just a formula from BitLogic that lets you take 2 unsigned integer values, in my case 0 to 255, and find their average without having to worry about overflow. And the formula is you take A and you do logical AND with B, and you also take A and you do XOR with B, shift it 1, add those 2 parts together, and you'll get the average of the 2 pixel values. And doing this with SIMD, I can apply this operation for 64 pixels at once to get the average. And then it's like five steps. Doom, 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 64 done at once. The other thing that happens is the pixel rows, my goal is to only have them be 1,000, but I let them get almost to 2,000. And then when they get to 2,000, I shrink them back to 1,000. So I have pairs of pixels that I now need to average into 1 pixel. And there's a wonderful SIMD operation called deinterleave, which lets me take 128 bytes, 128 pixels, which are 128 bytes, and in one step turns it into 2 64-bit byte slices, where the first one will be all the even bytes, and the second slice will be all the odd slices. And again, that's a single SIMD operation, and then I can do other things to do the average in groups. So I have some tips for SIMD optimization. I really like the portable standard SIMD library that comes with Rust. Its only downside is that it's a nightly feature. It's not part of the stable standard yet. But its upside is that you can write this SIMD code and it can automatically compile for x86, which is what I'm running at home, for ARM, and even for WASM. I mean, who would have thought that WASM has SIMD support? But it does. And this really will make WASM programs. This program has a mode that runs in WASM and it makes it run faster. If you'd like to learn more about using SIMD in your code, I have an article called 9 Rules for SIMD Acceleration of Your Rote Code. I wrote it like a year ago and then reread it while I was doing this. Thought, wow, this is a good article, just what I wanted, which is, of course, why I wrote it. Let me call out a particular function that's related to the SIMD library, but it's in a different namespace that's super important, and that's the asSIMD and asSIMD mutate operations. And 2 reasons to call them out. 1, they're really important, and 2, they were contributed to the library by Scott here from the Seattle Rust user group. So thank you, Scott. The other trick I did to make the SIMD run faster, as I said, the Turing machine has vectors going off in 2 directions to represent the unbounded tape. Instead of using vector, I actually switched to using aligned vector, and that meant that I didn't have to do quite as much setup when I wanted to do the SIMD operations on the vectors. So that saved a little work and made things faster. But how much faster? Did all this. The SIMD will make its operations often like 5 or 6 times faster, but the whole visualization program isn't doing those operations all the time. So the total effect was 40% faster, which is good, but still would reduce the runtime for doing 10 trillion visualization steps to be 1 year, 8 months, which is still too much. So that still wasn't fast enough. So here's the second speed up I did, and that was to switch my algorithm for taking a row of the tape cells and turning them into a row of pixels instead of having it do that from fresh each time to make it incremental. And that's based on the observation that from one step to the other, the Turing tape can only change in at most 1 cell. A 0 can turn into a 1, or a 1 can turn into a 0. And because the tape can only change in one place, when we shrink that down to rows of pixels, only at most 1 pixel can change. So instead of recomputing, turning a whole tape into a row of pixels, now I copy the previous pixel row and then recompute just the 1 pixel that might have changed. And that had a really good speed up. That made things at least 25 times faster, and that got my runtime down to ballpark 24 days, which is maybe almost tolerable. But it still wasn't that good. So the next thing is I've got a 16 processor machine, 16 physical processors. So why not use multiprocessing? It was so frustrating to be running the visualization that we saw before and look at my CPU meter and it's like at 3 or 7%. It's like I've got all these processors and they're not doing any work. The problem is that Turing machines are notoriously sequential. I think it's theoretically impossible to use parallelism to speed up Turing machines. So it seemed hopeless, and I didn't do anything about it for a long time. But then I realized that even though the Turing machine is sequential, visualization isn't necessarily sequential, and the visualization was actually 50 times slower than the Turing machine. So I really only needed to parallelize the visualization step. And the way I did that, we can see from the picture. So say this is the picture that you're working on rendering with 10, it says 100 trillion, it should say 10 trillion. Maybe, well, wherever it is. This is the picture you want to render. We divide the work for rendering this picture into, say, 32 parts. And then for each of the parts, say part 30, we run the Turing machine in kind of a headless mode without doing any visualization until it gets to the step that corresponds to the start of that part of the picture. And then it turns on visualization, does visualization for just that segment and stops. And when we're doing visual, and then we have 32 of these images, and we can just carefully stitch them together to get the main picture. And if I do that, then I get this happy circumstances where my CPU meter is now going at 75 or 98%. And that makes the whole thing 11 to 15 times faster. So it gets the runtime down to, the actual runtime was 50 hours, 38 minutes, and 24 seconds. So with that, I set what I believe is a new world record for doing Turing machine visualization that does this full pixel averaging. And that's because I did that starting last Saturday night, and it finished Monday night. And I wanted to set a new record for the Seattle Rust user group. So as far as I know, the old record was to render out to 10 trillion steps. So this time I rendered out and visualized to 10 trillion and 1 steps. And we can see the result here. And there we go. 10 trillion and 1 visualization steps. So let me end with kind of status and some links. First of all, there is a WASM version of this, and you can play with it and get access to links with this QR code. It runs in your phone. It won't run to 10 trillion in your phone, but it will run in your phone or on your, just in a web browser. It's kind of cool. That's the web visualizer that's available on GitHub. Also, happily, if you go to bbchallenge.org, any page on that website will show a Turing machine, and there'll be 3 buttons at the bottom. One of the buttons says Blaze. If you click Blaze, that will give you this Rust visualizer. And it doesn't have as many features as the other visualizers, but it's more colorful and is very, very fast. And can go for many more steps than the other visualizers. The whole project is available on GitHub. There are 2 articles. There's an article that covers this material, how to optimize Rust for slowness and some of these speed up tricks for visualization. And there's also an article on how to make SIMD faster. I have a YouTube channel where I just very low traffic on, but it is where I put these visualizations from time to time. I've recently added and looked at 2 new features. One, the BB Challenge org has moved from working on this 5-state and 6-state machines, and now they're looking at 3-state machines, but they can write 0, 1, or 2 to the tape instead of just 0 and 1. And they're also looking at 2-state machines that can write 0, 1, 2, 3, or 4 to the tape. To visualize those requires more than just monochrome colors, so I added a generalization to the visualizer that can handle multiple colors, and that's what's running now on GitHub and on bbchallenge.org. And the other thing I looked at, because of a comment on the Rust user group Discord about compiling regular expressions, I thought, well, that sounds useful. How about doing something not quite as useful. So I've recently been working on compiling the Turing machine runs, not the visualization, right into x64 assembly, and that gets me a speed up. So to visualize, not visualize, to emulate 10 trillion steps with the Turing machine with Rust was taking like 6 hours. To do it with this with Rust as a host, but running this compiled assembly code gets it down to just about 1 hour. So that's my talk. Thank you.